Good afternoon, everyone, and welcome to the lectures on quantum field theory. And this is now chapter 11 on path integrals. And as I've always told you, please also read the the books of Michio Kaku, Mandel and Shaw, and F. Gross. They all have books in quantum field theory, so you'll be experiencing more difficult discussions, more difficult problems, and more tricky examples for this course. But I'd like to also remind you that the lecture series that we have is a simplified version of quantum field theory, so you just have to get more rigorous experience in these books in particular. So we will now start with the quantum field theory on this is the 11th chapter, path integrals. So path integral approach to quantum field theory is very helpful in advanced contexts like string theory, and it is also the method used in calculating amplitudes for a quantum transition from one state to another. But before we do path integration, how the path integrals were derived, let's start with Gaussian integrals first, because practically everything boils down to integrals known as the Gaussian integral. So this is a Gaussian plot, a plot of exponential to the negative x square. So this is the plot. You have like a bell. By the way, this is also another way of writing e to the negative x square. So here the plot is very localized. It is like a bell again, and we can actually compute its area here under the bell. But however, this is a little difficult, but yeah, they managed to solve it using polar coordinates. So we set the area under the curve to be of this integral. So we start with getting the limits from negative infinity to positive infinity, and then we integrate with that limit e to the negative x squared dx, and we set that as I. So this is very nice looking, but it's a little bit tricky to solve this one. By the way, the x here is a dummy variable, so you can just replace it with like the same integral comes out when the same result comes out when you integrate on the y-axis. So they're the same, or even in the z-axis it's still the same. So to solve I, we can multiply two Gaussian integrals like this. So this is now I square, and of course you can simplify it to this one. So you have a product of two differentials here and the product of the functions that are going to be integrated, and they have the same limits. This is supposedly equal, you have another integral supposedly, but of course they have the same limit. You can just write general integral with limits negative infinity to positive infinity. Then we change to polar coordinates. As you can see, you have x and y there, and x and y is just equal to r square. It's just equal to r square. And of course, in polar coordinates, you have x equals r cosine theta, and then you have y equals r sine theta. So if you draw it, this is your x and this is your y. So here is your x and this is your y. This is your r. And your theta would be this one, theta. So that's how you do in polar coordinates. And so your r square is equal to x square plus y square. So you can write that as r. And now dx dy is an element of surface area in the xy plane, but in polar coordinate it becomes r dr d theta. So you have to replace that here, and then you have now a simple integral of r. So in the xy or in the Cartesian coordinate system, you are integrating over the whole area, negative infinity to positive infinity. So in order to cover the whole area, you have to integrate with respect to r, but covering the ranges from 0 to infinity, so that you will really spread out the area from the origin to the end of the area, and that's infinity. And of course, your theta, in order to cover everything, so you have to go from the origin to infinity, and then the area should be covering everything. So that's 0 to 2 pi. So in this case, you will have you can change variable for your r square. You can write u as your r square, and that your du will be 2r dr. So this will now be over 2 here. So you replace with this one du over 2, and then you replace this one with e to the negative u, and then you integrate it, and this is just the same function, negative of this function, and so you'll be able to get 1/2. Now let's proceed. So our I square in this case would be given by so overall you have this as 1/2, and this one would be 2 pi. So I square would be pi, and so I would be square root of pi. So this is now our integral. How about for this one? So here you can let your y square to be ax square, but hey, don't get tricked. This is just I just made this like that, but actually what I really mean is that your y should be equal to square root of a over times x. So your dy would be equal to dx, and you have square root of a here, so that you'll be able to change this thing, this thing with this one here. So Let's make it cleaner. So y is equal to square root of a times x, so that your dy over square root of a is equal to dx. So it's now equal to, this one is square root of pi, and so you will have overall the integral of this one is square root of pi over a. Now, as you can see, we also have this kind of function if you would later go into more literature. But for n equals odd, for n equals 1, for example, then you would have this function. And so that function would be looking like this. And for n equals 3, the function would look like this. So for n equals 1, it is this one. And for n equals 5, it is this one. As you can see, you have an area, positive area here, which is equal to the negative area here. So when you add them up, it's equal to 0. The whole thing is equal to 0. The whole area. But if you choose n to be even, then it's a different story. By the way, for every n that is odd, so you will have an integral that is equal to 0 for x to the n e to the negative ax squared dx integrated from negative infinity to positive infinity. But of course, it's not 0 when it has limits. I mean, especially when the lower limit is not the same value as the upper limit, it would be not 0. But in this case, for negative infinity to positive infinity, it's 0. Now, looking at this, if you have this function and you make a derivative with respect to a, by the way, you can interchange this and this one. So you can actually write this as integral from negative infinity to positive infinity derivative dA, because the integral and derivatives are commutative. So you have e to the negative ax squared dx. So you can get the derivative of this, which is just this one, and of course this one is also equal to pi over a. So if you get the derivative of this, you will also have a derivative of that one, resulting to negative square root of pi over 2 times 3 to the 3 halves, a to the 3 halves. So if you equate the 2, then you would have this expression. So if you look at integral of x squared e to the negative ax squared dx, it's just this one. The plot is here, so you have positive areas here, so they add up, and from negative infinity to positive infinity, the area is not 0. And of course, this is for x to the 4th and negative x squared, and this one is the original Gaussian function. So in general, if you do an iterative procedure, you will be able to get this one here. this expression. So for integral of x to the n times exponential of negative a x square dx, then you would get this one, this expression. Another very important Gaussian integral is of this form. As you can see, you have a linear term with respect to x here, and that's bx. So what you can do is to complete the square. In this case, you will have completing the square. By the way, we missed something here. This is supposed to be just a, not there's no 2 here supposedly, and so there should be a 2 here, and this one should be that one. But anyway, if the procedure is correct, but the correct answer here would be equal to e to the b square over 4a times square root of pi over a. So that is actually the correct answer. So for n dimensions, a Gaussian integral would look like this one. So the x here would be x would be a column matrix, so xt is just a transform of that matrix. In general, if you have complex elements of x, then that would be the adjoint of x in general. So this would be adjoint. So A there is a matrix, n by n matrix, and you have there the elements of coefficients, and yeah, your dn there would be, your dnx would be just the product of all the dx's. So if you just have two-dimensional matrix, then the form of your A would be this, and your X would be here. By the way, before we go to that, let me just also add some integral here. You also have integral of e to the negative ax square plus bx plus c dx is also equal to square root of pi over a exponential of b square over 4a plus c. So you also have that. So we now continue. So our x transpose times a times x would be given by this one, and so we will have this one, and then finally we will have this form. So what is particularly done here is to complete the square and subtract what was added when the completing this square was performed. So finally you will have the answer to be given by this one for this particular matrix. But this one here is the determinant of this matrix. So in general, this one, in general, the integral of this is just equal to this. Pi to the n over 2 over the square root of the determinant of the matrix A. So this can be extended to this one here. So I just would like to make this bigger. So this is actually what will be used in quantum field theory, your higher dimension Gaussian integrals. So going back, we will now go to the Feynman path integrals. So we will now discuss about path integration, and what is actually the goal here is to reduce the path integral to Riemann sum. So again, the path integral is a method in which we are able to calculate the amplitude for a system that starts off in some initial state I and end up in a final state F by adding up amplitudes of the system to pass through all possible paths from the starting point to the final point. So this, if you have a initial point and a final point, there are all sorts of paths you can go in a straight line, you can go in to this kind of path, or you can go to the final point with that path, or even this path. So you add all of those things, you add all the paths, and then you're actually getting the total amplitude. By adding all the paths going from the initial point to the final point, you're adding all the amplitudes of the system, or the amplitude of the path in which the system goes through from the initial to the final point. So for example, the path can be or the path integral can be constructed by considering the amplitude for a particle to pass from point x sub o to a point x to the n, where n is the final and the o represents the original point, or the initial point, or the origin. If the dynamics of the system are described by the Hamiltonian H, then the amplitude is written here using this expression, with this expression here. So for a free particle, the Hamiltonian would be H would just be equal to the kinetic energy, or equal to p square over 2m, and of course the p hat there would be the momentum operator for the wave function representing the particle. And so if you apply that momentum operator, then you'll be able to get the momentum of the particle represented by the wave function. So going back to this one, to write the amplitude in for this expression, that's the amplitude. So we consider every possible path from x sub o to x sub n. And we start by splitting up the path into smaller pieces and then use the limiting procedure. So we split the path. This is what you call time slicing. So we slice the time into n parts, going from x sub o to xn. So we use this. We slice the time. Then, so we have our t to be equal to n times delta t. And this is just this one. So you can actually write everything in expanded form with n factors. N factors. Now recall the fact that the position eigenstates form a complete set of states. So if you recall in your quantum field, in quantum mechanics, you have this one in the, that's just equal to 1, or the identity matrix if we have a row matrix representing the x. So again, we split up the internal interval into n parts, and each little part will be a complete set of states. That is this one. So we can put this expression in between, and which doesn't actually alter the expression, because this is just equal to 1, and if you multiply 1, it's just the same thing. So you have I here, I here, I here, and I everywhere. So you will replace that with this, each I, and then this one, and yeah, that, and this one in this expression. And now we collect all the integral dx, and we multiply everything in a compact notation, and so we'll be left with these. And look, what are these? These are just the amplitude from for this case, from a point, the nearest point, x of n minus 1 to n. This is actually coming from x sub 0 here, and then since you slice the time, you have amplitudes going you have amplitudes for all the segments in the sliced amplitude, time sliced. Now we calculate each individual term by bringing up the Gaussian integrals, and we recall that the momentum eigenstates also form a complete state, this one here. However, there is a coefficient of 1 over 2 pi there. And we also note, if you go back to our lecture in chapter 1 or chapter 2, I guess you will find this. You also find this one. It's just the conjugate of the other. That's the inner product between x and the momentum, or the momentum and space, or space and momentum. And so you have this, your Hamiltonian operating on P would just be P square, P hat square over 2m operating on P is equal to, yeah, this one. And then of course there is, if you raise it to exponentially, so you also have this one. So each expression here, each of the expression here will have the form that could be easily integrated. So this one, or should I say, this one can be written as this one. And so if we look at it, your P will operate on this, and this will just be equal to this expression. And you can let your dp be out of the integral, and also this one here. So what's left is this one, which is just equal to exponential of ipxj, and combining with this you have you will have this expression. And so anyway, you will have this one. So this will now be easy to integrate because you now have a Gaussian integral here. So you have an exponential that is in the order of p square, negative p square, and then this is just when you erase this one, this will just be plus that one. And so that is just the Gaussian integral that we discussed earlier, and we'll have the form of this one. So using this one, this expression to each term of the product here, to each of this one here, for this one, and so on. You will have n terms of them, and so your amplitude, which is originally this one, can be written in terms of this. So you will have a product of all the I m over 2 pi delta t with this one, and this one also. All the terms similar to that, where of course you're now writing the limit where n going to infinity here. And of course by letting your delta t here going to 0, that becomes dt. So this expression becomes dx dt, or x dot, time derivative of x, which you are going to substitute here. That's why it becomes this one here. And of course, since you now have continuous um, continuous expression, your summation becomes an integral. So here you have that. So now we have this expression. And the path integral measure that we will have now would be this one. Leaving only this, which is just this one here. So the path integral then can be written as a compact expression. Uh, so we now have this expression for this integral, path integral. So in this case, this shows that the amplitude for a particle to take the path from x above to xn is proportional to the exponential of the action s, which is just this one. And the free particle, by the way, was considered to have a Lagrangian of 1/2 mx squared. So we've seen that in the example that we did, or in the calculation that we did. This is a very good result, and this will actually be the same for quantum field theory, tying up in this case you have quantum theory and classical expression in a quantum theory. So in general, the amplitude for a system with Lagrangian L, or also in other space, momentum space frame, you would also have a Hamiltonian instead of the Lagrangian. But anyway, for if you want to get the amplitude for a system with Lagrangian L, that means, of course, that's kinetic minus potential energy of the system. It's just you just have to use this expression, and you will be given examples in the next part of the lecture. I mean, in the next meeting, examples will be given by all of you. So in quantum field theory, a path integral is used to compute the amplitude for a transition from a state phi 1, that's of course dependent on, phi 1 is a state time t1, to state phi 2 at time t2. So you will have this expression for this thing, for that thing, for the amplitude. So if we say phi 1 is equal to phi 2 equal to phi 0, be the ground state, then the energy of the vacuum using path integral methods can be calculated then. So, and also when an external source Jx is present, the path integral becomes this. You just add this expression to the Lagrangian. and we define the vacuum to vacuum amplitude to be equal to this. So as a summary, path integrals is a method that can be used to calculate the amplitude for a system to transition from one state to another by considering all possible paths between two states. Path integrals can be used to calculate any quantity in field theory, such as the vacuum expectation value for a field. The use of Gaussian integrals is important in the calculation of path integrals. So you have to remember all those Gaussian integrals that we have discussed earlier. You can also take this quiz, and probably you can also do number 3 in particular. So this is it, guys, for the for this chapter. We will move on to the next one in the next meeting. I hope you learned something in this lecture.